Hello and welcome everyone. Hello, hello. And start. Wow. Nice to see so many of you here. Hello, hello. Yes, hi. Thank you very much. Welcome to my talk on coupling, cohesion and change. We will be talking about spaghettification, coupling, cohesion, change, wormholes, hexagonal architectures. We have a framework, we have team topologies, we have a lot to digest. So let's get to it. But first, let me introduce myself. I'm Boyen van Gorp. I'm a father, I'm a husband, as you can see. I live in Ede, and I'm a software quality expert at Alliander. Oh, and I play Irish music on the accordion. I do that as well. And software quality expert means it's basically a staff engineering function, and in my role, I need to go to teams. I analyze their software, and I let them know something about the risks involved in their software designs, and then I help them with improving that. And that's also sort of the reason why I started working on this framework. It started with these two words, it depends. Okay, so when I started as a junior software engineer, I was reading a lot about best practices, design patterns, and I would discuss this with my colleagues. And so I would say, okay, what's the truth here? I have write everything twice and don't repeat yourself. And they would tell me, yeah, well, it depends. Great. You hear this very frequently in software. But what does it depend on? And then they would tell me, yeah, sure, it depends on the context. Again, very helpful for me on the context. So now, flash forward 10 years, as I said, it is my job to explain to people why it depends, on what it depends. And this means that I need a framework to evaluate software, but I also need the vocabulary to explain to others why there are risks involved with software designs, why one choice is better than the other for a certain context. Okay. So I came up with a framework, a mental framework, and at first I had no intention whatsoever to put it on paper. And then this person here said I should present it. So that's what I did. I put it on paper, and it gives me a pattern language, and my team as well. It allows me to do trade-off analysis. It helps me to understand and explain best practices, which I will show later. Identify anti-patterns, and it's also skill invariant, which I really like, because it means it's fundamental. It means, I call it component in the presentation all the time, that it works for methods, classes, modules, architecture, but also it works in organizations. So I like that. And this is the framework. A lot I will be discussing today, and I won't do that all at once. I will break down the problem, as we software engineers do. And we start with coupling, cohesion, and pain, the main topics here. So for coupling, just let's go through the definitions real quick, that we're all on the same page. Let's have a ubiquitous language together. Coupling, connected, the degree of dependencies. So can you make a change in isolation, or do you need coordination, right? Can I make my change locally, only in my method, or do I need to change it in several spots? Or perhaps do I need to make this change, and somewhere else in another application a change needs to be made as well? Can you easily break down your application into microservices, or yeah, or perhaps a modular monolith? That's coupling. For cohesion, we are looking at when components have proximity, there's also unity. And I really like the definition of simple to explain this. And this is a reference to Rich Hickey, who had an excellent talk on simple made easy. And what he says is, simple, that's one role, one task. It's one, and I like one. It's very simple from easy, because easy means that you can understand it, and then it's easy for you. For me, it's easy to solve a Rubik's Cube, but it's only easy because I learned 144 algorithms. That's not simple. That's not one. So cohesion, simplicity. For change, we look at the rate of change. And changes introduce risk. And that's sort of obvious. So if you have a stable system and you are making a change, then there's a chance that something breaks. That's one. But it goes a bit deeper than this. Change is actually quite important. There was research on this as well. In 2006 was the first time this was researched, I believe. It was from Microsoft. And there was a release of Windows Vista. And Windows Vista was not their best release. There were some bugs, quite a lot of bugs. And they decided, well, what is the root cause of all this? So what you would expect, or at least what I would expect when I was starting with reading this research, I would say, oh, it's probably complexity of the code, cyclomatic complexity. It might be the lack of unit testing. It might be that there are too many junior developers in the team and they need more guidance. But actually, the main significant contributor was code churn. And code churn basically means that you have this component, you have this method, class, and it's being rewritten over and over again. And the more this class is being rewritten, the higher the chance is on bugs. This research has since been replicated many, many times. Code churn is really one of those most important factors. And then we get to pain. And pain happens in many ways. So, for example, you could have security pain. You are being hacked, right? That's pain. You could have performance pain because your application is not performing. But within the context of this talk, I'm talking about maintenance pain, about reliability pain. So it's difficult to make changes. It's difficult to understand the code. You need this increased coordination to make your changes, and your changes are slow. And that brings me to the formula of pain. And this is just a mental model for me to evaluate, will there be pain or not? And I came up with a new term, and I'm quite proud of this. I call it spaghettification. And this is this feeling that I think each of you has had when they looked at the code base and they're like, oh man, I don't want to touch this. Although I know there are some people that really like to be in this code base and they want to change it and they want to make it tidy and nice. And basically this coupling and cohesion, or actually the lack of cohesion, is what really contributes very strongly to this spaghettification. And then you also have the amount of change, right? So when you're making changes, every time you make a change, depending on basically how complicated your code is, what you say with the spaghettification, you will get pain. You have a chance on pain. So what's nice about this formula is that you can do two things. You can either make sure that you don't make changes, and we see this in legacy software. Basically, we say, okay, there's a feature stop. There's too much risk involved in making a change here. We'll just rebuild it. Or we need to ensure that we have a low coupling and a high cohesion. Finally, we just accept that we have a lot of pain. Okay, so let's see what entails this spaghettification. And let's start with coupling. We'll go over the dimensions. And the first dimension is strength. So strength is about how tightly components are bound together. And when they're very tightly bound together, when you have very tight coupling, it means that you have a lot of shared knowledge between these components. And that makes it difficult to make a change in isolation. So the highest form of coupling strength is intrusive coupling. And basically here you're touching private information of another component, which you shouldn't be doing. So an example here would be reflection, right? So you're reflecting on some library, that library is changing, there's nothing that goes off, right? Well, your unit tests, luckily, but it's very implicit, right? Your code will compile, everything seems fine, and then you get a runtime error. Another example is that you get an interface from another module, from another component, and this interface, you're hard-casting it to a specific type, so you can use a specific method on that interface. Very evil, that's intrusive coupling. Functional coupling is when you have shared business logic between several components. And you can identify this when you see, for instance, in Git, you have a new business requirement, and you need to make a change in several places, right? So then they're also coupled, but it's, again, implicit. It's not an actual physical coupling. So when you look at, another example is duplication. Right, so when you have duplication, and it's actually only when you have duplicated business logic, that is when you also see the functional coupling. Because if you have this duplicated business logic, you need to change it in several places as well. Okay, so these two are in the category of wormholes. And there was a great blog by Jules May, which I really love reading. And he came up with the term wormholes. He was working on a project. It was millions of lines of code. It was written by 20 developers. It was written in 4 languages, C#, Delphi, C++. And most of all, there was a bug list of 4,500 items. And instead of just fixing it, he, for science, for us, started classifying these bugs. And what he found was that 94% of these bugs were wormholes. Okay, so what are wormholes? Basically, you are changing something in A, And for some reason, in M, L, and Z, something breaks, right? That's what he calls a wormhole, and basically that's in the category of intrusive coupling and functional coupling. Slightly lower level of coupling is data coupling. What we're doing here is that we have this shared database, we have this shared data model, and when this data model changes, then you need to make changes in other components. Again, this is something we see quite a lot. What happens then is that you have this weekend that the changes need to be made. There's a draaiboek, a playbook, right? Everyone needs to work in the weekend, and then on Monday everything hopefully works again. Because all these applications need to be changed because they're all relying on this database data model. And basically what we want to achieve is contract coupling, right? So components are decoupled by clear interfaces. And as long as this is a stable contract and it doesn't change constantly, this means that you can evolve independently. So that's the first dimension. The second dimension is distance. And basically what we're saying here, what is the physical or logical separation between components? And logically here, so let's say you're making a change in a method and you're coupled to something within the method. That's no pain whatsoever. That's simple. And even within the class, and maybe even within the same namespace, that's fine. But when you are coupled, and especially when it's functional coupling to another application, or even something external of your company, then you require a lot more coordination when you are not coupled by contract. So distance is really important as well. Finally, we have connectivity, and this is about sort of the quantitative aspect of coupling. It acts like a multiplier, and I make 3 distinctions here. Communication fan. So let's say we consider the yellow component that is the one we are analyzing. And when we talk about the fan-in, basically changes in the red components affect the yellow components. And if you talk about communication fan-out, changes in the yellow component affect the green components. And the worst type of communication fan is when you have both, right? So you have a change here, it affects your component here, and this affects all the other components. You get this cascading effects, and you need to make changes all over your code base. Very undesirable. This is like the spiderweb architectures that you see sometimes. A bit zoomed in, communication density is about the number of connections between 2 individual components. And the denser the communication is, the tighter the coupling is going to be. And a worst case scenario is that you have communication back and forth, right? So that you get this circular dependency, you make a change in A, it affects B, and B affects A again. Finally, we have the communication surface, and this is the depth of the interface. And this is a term coined by John Ousterhout. He's the writer of A Philosophy of Software Design. Excellent book. And basically what he coins is, let's say we have 2 components here. And they both have an interface, and they both have private information. And the area of these 2 components is the same, and so they have the same amount of functionality. For the left component, there's a shallow interface with a deep module. And basically what we're doing here is that we are limiting the coupling points of this module, and we are also making sure that the complexity is hidden away, right? For the right example, we have a very deep interface. Yeah? There's many coupling points on this interface, and actually we're not really hiding any complexity away whatsoever. Okay, so coupling is nice, because you can, if you are aware of the coupling that you have, you can play with it. So if your distance tends to 0 when you have your coupling in your method and your class, as I mentioned, it will also tend to 0 in this formula when you have contract coupling. So basically you can negate the pain from coupling by making sure that you either have contract coupling or you're keeping everything close together. Connectivity, unfortunately, doesn't work that way, because if connectivity would be 0, it means there's no connections, and if there's no connections, there's no coupling. But while connectivity cannot make a bad situation better, it can definitely make a very bad situation worse and worse and worse, right? So the biggest problems that we find is when you have both a coupling problem, but also a high amount of connectivity. Okay, that was coupling. Let's go to cohesion. So when you think about cohesion, you need to think about the limits that we as humans have. And this is described by Miller's law. It's a number you can keep about 7 ± 2 objects in memory at the same time. And if it goes above this number, it becomes very difficult to make reliable changes because you don't have full understanding. Okay, how does this relate to cohesion? I said already, cohesion is oneness, right? It only does one thing. So it means that it also counts towards this Miller's law as one. The moment you are intertwining concepts, you keep that in memory, and it doesn't count as one anymore. It means that you can keep less components into memory. So, what do we have for the dimensions of cohesion? The first one is weakness. How related are the tasks within the components? And basically, if it's weak, there's an increased cognitive load, so it's more difficult to understand, it's more complex, and it increases the risk on unintended side effects. And this is because when you put stuff close together, the chance that it affects the other component increases. So the first level of weakness is accidental cohesion, and this is when tasks within a component really don't have anything to do with each other. A prime example here would be a utils module. We don't really know where to put it, so we just put it here. Another example that I've seen in code is when a class is called a manager. And I'm looking guilty. If it's very difficult to name your class, you sort of get the idea, oh, do we really have cohesion in this class? For logical cohesion, your components are grouped by a task, but not necessarily for the same purpose, not necessarily for the same user story or epic. So we have, for example, we have all our business logic in one module, even though it might serve several user stories. We have all our repositories together. We have all our controllers together. Model cohesion is similar. Here, your components are working on the same model, but not necessarily, again, for the same epic or user story. So this is what you see in Java when you have your person service. I'm working on the person class, and all logic related to persons I put together, even though they might serve different user stories. For functional cohesion is basically what we want to achieve. So we're working on the same data, it's all working towards the same goal, and the tasks are related to each other. Okay, so a second dimension of cohesion is convolution. How simple is it to make changes? How simple is it to understand what was written? And I like to differentiate between internal convolution and external convolution. And I coined the term entropy for internal convolution, which is basically there's disorganization, chaos within your component. It's complex to understand. There are many paths through your code. There's a high amount of call chains, decision points, so it's complex to understand what's going on here. Whereas fragmentation is more about, I have this cohesive logic, and it's spread across several components. And this means that it's very difficult to apply local reasoning. You cannot reason what's going on within this class without a broader view of the system. And local reasoning was a term that I wasn't familiar with this a couple of years ago, so let me just quickly explain that. Basically, let's say you have a counter class, and this counter has an internal count and an increment method, and a method that has a get result. And basically, if at any point within my application I want to know what get result will give me, I need to know a couple of things. I need to know where is increment being called first. I need to know if this call is before or after I call get result. And I also need to know if this is being called in a multi-threaded environment or a synchronous environment. So I need to know a lot about my application context before I can reason about this. So I cannot apply local reasoning here. Misalignment is about differences in implementation direction. So, and here we have two types again. Structural misalignment, so when your technical standards and direction is misaligned. So for example, you have a different coding style within your agile release train or even within your team. There might be different integration patterns within your team or agile release train. So for example, you communicate through Kafka, you communicate through S3 DOMs, you communicate through SOAP, REST calls. That basically gives structural misalignment because it becomes more difficult to work together. Semantic misalignment is about that there's no agreement on the domain meaning, right? So if you put a person inside your application as a class or an entity, depending on your domain, it can have a very different meaning, which is solved sort of by the ubiquitous language, where it says you conversate with your business, and together you decide on what term you use for a certain entity, right? So in the sales domain, a person might be a customer, and in the HR domain, it might be an employee. Okay, so cohesion, it's not as nice as coupling because it doesn't tend to 0. It tends to 1 at minimum. You cannot say, oh, I have a very high functional cohesion, let's just make sure I have very low entropy, unfortunately. So if you have functional cohesion, it tends to 1. The same that if your convolution is low, it tends to 1 as well. And the same comes for alignment. So unfortunately, we cannot play with this. But let's say you have a very complicated algorithm. And if you are aware of this, at least make sure the logic is not fragmented all over your code base. Because you're already imposing a very high cognitive strain on the person reading your algorithm. So make sure that you make it easy on your coworkers by making sure there's semantic alignment, a lack of fragmentation, and functional cohesion. Okay, let's go to change. Change has more aspects than I name here, but I think these are some of the most important ones. And with change, what I mean is that we're trying to manage the amount of changes made to the code. And we can do that in several ways. One way is that we distinguish between roles inside your component. And here I'm borrowing from domain-driven design again, where they differentiate between subdomains. So you have a core domain. Your core domain is basically, this is your business logic, right? It's differentiating for your company, for your team. And the change here is driven by changing business requirements. So it has its own cadence. For your supporting domain, this is basically supporting your business domain. It's not necessarily differentiating. Many applications might be using it. And it's advanced, if you have an advancement in technology or if there are security updates, that's when you get changes. So an example here would be Kafka, or it would be your object storage, your load balancers. It's really your supporting infrastructure. And finally, you have the generic domain, and these are basically your solved problems. And these don't change a whole lot at all. We've seen an update on Log4j some time ago, but usually it's only your security updates when it really changes. So when you look at a component and basically where it is in its current life cycle, your core has the most changes at the start of the early stage development, right? So this is where you get a lot of business requirements. Whereas your supporting domain has a constant stream of changes throughout its life cycle. You constantly get your updates. And the same with your generic domain, but you will get less updates because there won't be any functional changes there. All right. So for generality, it's about how well a component is designed to handle a broad range of use cases. That doesn't necessarily mean that you should always write generalized code, but it means that if you want to limit your change, generality is one way to do it, right? So you write something, and it's very good at what it does. It perfectly captures your domain, and it just has this one task that it does, right? And if you want to change the behavior, for example, you inject something. For instance, logging is very general. It can work with everything. Finally, we have defects. And defects is on the one hand obvious that it has an impact on change, because when there's a bug, you need to change your code. But there's something deeper here. So it's very important to get this first time right. And why is that? This article of Jules May explained it, but also the research by Microsoft. So what he found was, in this code base that he was analyzing, and also code bases he analyzed afterwards, he saw that the second generation bugs outnumbered the first generation bugs about 3 to 1. And so a first generation bug is when you have a bug in the initial code. So the original author had caused the bug. But the second generation bugs basically happened when a bug was trying to get fixed. And when I was thinking about this, so his conclusion was, it turned out fixing bugs created more technical debt than all other causes combined. I was like, oh, wow, that's something to digest. And I was thinking about this, and I only have hypotheses here, so I don't necessarily know the answer. But there's two aspects here. One, when you have a bug, you are somewhere where there's a lot of convolution, right? Somehow there's no cohesion, because otherwise this bug wouldn't occur. The original developer didn't understand what he or she was doing. But also, when you are fixing a bug, in what state are you at that moment? Are you calm, relaxed, or are you under stress, right? And once you are under stress, it means that you get tunnel vision. Once you are under stress, your cognitive load, your maximum cognitive load decreases. You can keep less objects into memory. So I think this might be why you found that there were so much more second-generation bugs. Okay, so this was the whole framework. And that's a lot to digest, I think, but I'm going to just put this into practice and perhaps help you to familiarize yourself a bit with these concepts. And we'll look at 3 levels. And first I'll talk about solid. I picked solid not necessarily because I love it, but because I think it's fairly clearly coupled to coupling, cohesion, and change. So when we look at single responsibility principle, it says separation of concerns. Gather together the things that change for the same reasons, and separate those things that change for different reasons. Okay, so we're saying here that we need to put together things that are same-ish, for the same purpose. And that's basically our functional cohesion, what we are trying to influence here. It also says single responsibility. Well, responsibility is a term we heard before. That's part of the entropy, right? If there are more responsibilities of a certain component, it means that it becomes more convoluted. But at the same time, and this is immediately the main criticism, I think, on the single responsibility principle, is that when you're making your components really small, it means that you need to read many components to understand what's going on. So while it's affecting your entropy positively, it is affecting your fragmentation negatively. If you take it literally, dogmatic, right? Really single. So another aspect here, and I think that Robert C. Martin, who wrote Solid, tried to sort of, he tried to lessen the effect of fragmentation by putting together in there. Because when you put things together, even though it might be fragmented, things that are close together, if they have a low distance, it becomes easier to understand what's going on. At least don't put it far away from each other, because then it would be a mess. Finally, the single responsibility principle also does something with separation of concerns, and the word change is in there 2 times. So let's say that we would not be separating our concerns. Let's say that we put our core domain, our supporting domain, and generic domain together. What does that mean? Well, it means that your code suddenly has a lot of reasons for change. And when you're changing your code the whole time, it means you get a lot of code churn. Right? So it changes when your business requirements change, when you get an update in your supporting domain, and when you get an update in your generic domain. That is why we want to keep our concerns separated. Okay, for the open-close principle, it says software entity should be open for extension but closed for modification, ensuring stable, adaptable components in response to changing requirements. So basically here it's saying, right, okay, so I have this component, it's very good at what it does, and I don't really need a reason to ever change this. So by writing very adaptable general components, I'm trying to limit my change. I think this is an important aspect of the open-close principle. For the Liskov substitution principle, I learned it as if it looks like a duck, acts like a duck, and quacks like a duck, it is probably a duck. But if it looks like a duck and quacks like a duck, but it needs batteries, you probably have the wrong abstraction. And I think this is very much related to semantic misalignment. Right? So duck, the entity duck has a meaning within your domain. And if you're not consistent within your domain what your duck means, you will get errors, right? So is your duck a living being, or can it also be a duck with batteries? Or will your duck with batteries give you a runtime error? And I already mentioned this, right? So it also tries to affect the change because it also tries to affect defects in runtime. So for the interface segregation principle, we say no code should be forced to depend on methods it does not use. We are trying to limit our communication fan-in. We try to depend at a less amount of components, least amount. And for the second part, split interfaces that are very large into smaller and more specific interfaces. So basically we're saying here we are trying to keep our communication surface as minimized as possible. We want very shallow interfaces. Then for the dependency inversion principle, we're saying high-level modules should not import anything from low-level modules. Well, this has a lot to do with our role. So we have our core domain, our supporting domain. And the moment we do not keep this separated, it basically means that when your business domain, your core domain, depends on your supporting domains, you get the changes from your supporting domain in your core domain. We don't want that. And here it says both should depend on abstractions. That's basically what we want to achieve with contract coupling. By keeping them separated, we are influencing the amount of change in our system. So prior to making this talk, I didn't know that Solid was trying to affect so many of these aspects of coupling and cohesion. I thought it was kind of cool to see. Not just cohesion and coupling, but also change, which was unexpected for me. Let's have a look at hexagonal architecture. So hexagonal architecture is one of the first architectural styles that I learned. I will explain what it does and why it does it. It's from the mid-90s, and it was basically architectural style to combat common pitfalls in software architecture using object-oriented design. And immediately from the get-go, what it does is that it separates between a core, supporting, and generic domain. So it's trying to manage the amount of changes to each of the components. How does it do that? Well, first, okay, we have our core domain, and this core domain is fully functionally cohesive. So that's nice. It's easier to understand, simpler to understand. And there is a low amount of entropy because it only does one thing. It doesn't need to be concerned at all about the logic of your supporting domain. So it doesn't need to be concerned about your REST interface, your database interaction, your Kafka, nothing. It's just your core domain. How does it do this? Well, it employs ports and adapters. And basically what it does here is that you have your adapter here, and that communicates with the incoming port. This incoming port is an interface that's implemented by your core domain, by your business logic layer. So your adapter really doesn't care what's below it. You can change your core domain, you can change your business logic, and you don't need to change your adapter. Similarly, when you are communicating from your core domain through your outgoing adapter, you are communicating with an interface. Currently, this is a database, but it can also be a SOAP or a REST interface. It can be a Kafka stream. It doesn't really matter as long as they implement the same interface. So what we do here is basically that we're making sure that the communication between these roles is generalized. It doesn't matter what's behind it. We don't care about the implementation. How do you achieve this? Well, you will need an anti-corruption layer, which is also part of this. And basically what we do with our anti-corruption layer is that within our core domain, we have our model, our core model. And for our adapters, they have their own models as well. And within our anti-corruption layer, we are making the translation between these models. We are ensuring that in our supporting domain, you never know anything about the model inside the core domain and vice versa. So we're keeping that separated by contract coupling. A downside here is that we are increasing the distance by adding all these layers. And I think this is, again, the main concern with hexagonal architecture. Fragmentation. So when you look at the amount of steps on this level that you need to take to go fully through your application, start with the incoming adapter, which talks with the anti-corruption layer. This communicates with the incoming port, which is the interface. This is implemented by the business logic. Then you go to your outgoing port, which is implemented by the anti-corruption layer, and it goes through your outgoing adapter. So there's many steps to take here, right? And we're at 7 here, and now we haven't even taken into account that you might want to communicate with your infrastructure, your generic layer, right? So let's say there's at least 8 calls on this high level. That's really close already to this Miller's law, right? 7 plus minus 2. So I think this is the main criticism, and this is something you should take into account in your choice whether you want to employ a hexagonal architecture or not. Finally, let's go to team topologies, and specifically stream-aligned and platform teams. So let me go back. It was developed by Matthew Skeleton and Manuel P. in 2019, so it's quite recent. And it's basically to organize your organization. And again, here we can employ coupling, cohesion, and change. How it came to be, these stream-aligned and platform teams, from the original way of structuring your organization, which was functional teams and cross-functional teams. So if you have a functional team, basically you put all the professions together in one team. Right? So you have a platform team, security team, testing team, full-stack team, and a UX team. And basically, once one of the teams is done with their work, they throw it over the schutting. And yeah, good luck with that. So one of the solutions for this was the cross-functional team. So instead of having this schutting, we just put everyone together, and there's no schutting anymore, so no barrier, and that should solve all our problems. Okay, so when we look at the functional team, what are the downsides here? Well, on the cohesion part, they're not really, they're organized in a logical way, because they're all doing the same type of job within the team. And there's quite a lot of fragmentation, because to fully understand the application, you need to go through all these barriers. It's not within one team. There's a high chance of misalignment, because, well, it's difficult between teams to communicate with each other. It's much easier to communicate when you put things close together, if you keep your distance low. And also, there might be disagreements on the semantic meaning of terms. Right? So, and this gives us quite a high chance on bugs and defects. So how does the cross-functional team try to solve this? Well, basically, because they're all working on one product, the idea here is that they will have functional cohesion, because they're all working on that. It's not fully true, but we'll get to that later. And the amount of fragmentation will decrease, because it's all within one team. You don't have this barrier that you need to put your code over. And likely, because the communication is easier, there will be less structural misalignment and less semantic misalignment. However, there were also some criticisms on these cross-functional teams. One of those criticisms was by Martin Fowler, and he said, full stack and full cycle means that the team is often faced with an excessive cognitive load, which works against the desire for small, responsive teams. Okay, so what is he saying here? There is an increased entropy, increased responsibilities in this team, because some tasks are just too big for one team to tackle, which is basically our platform functionality. Right? So if you want to build your own deployment platform, you need a lot of specialization. Same for your CI/CD infrastructure or even your security pipelines. So that's a problem. For one team, some things are just a bit too much to contain. What I like about, there's a higher entropy. And what I like about this is that they basically took a software engineering approach on organizing their teams. Because if something gets too complicated, what do? We refactor and we make it simpler. And that's basically what happens here as well. We ensured with our streamlined team that the amount of responsibilities of these teams is limited, right? And it's only towards the product. So we split this up by splitting up the roles within the team. We have a core domain, which is linked to the business logic, and we have our supporting domain. And this is nice, because it allows also for the supporting domain to write very generalized software, which works for the entire company. Right? That's called X as a service, platform as a service, security as a service. They have redefined what their product is. It's an internal product. And this is fully functionally cohesive, because they're working on this product. And also, the structural alignment within the company will increase, because they're all working on this same as a service. So that's, I think, quite nice. Within the team also, the entropy is lower, because their responsibilities are lower. Okay, so we've discussed a lot today, and I just decided to put that all on one sheet, one handy cheat sheet. I will also be giving a mentoring workshop for 5-6 people later on in the day. And we will be discussing some more of these examples. Basically, what did we talk about? We had that coupling and cohesion are scale-independent properties. Coupling is multidimensional, and it can be mitigated if you are aware of what's happening inside your code base. Unfortunately, cohesion does not entirely work the same way, but if you are aware of a lack of cohesion, at least try to mitigate it, because it might be intrinsic. Your algorithm might just be complicated. And for change, I think especially this role and defects are really important. First time right is really important. And think about your limits. Think about that you have this Miller's law, 7 plus minus 2. And this is actually where you should make the decision, is my layer that I'm looking at right now going above this number? Perhaps I should start splitting it up. And yeah, that's how we can reduce our pain. So I hope your code may never reach high levels of spaghettification. Thank you very much for being here. And let's see. Can I take a picture of you? Yeah. If you don't want to be on the picture, then just cover your face. This is the second time speaking for me, so this is really special for me.